Okay, can we hurry up? Okay, good morning. So if you want the bad news or the good news first, so the bad news is you've got me twice again this morning, but the good news is if things go well, this will be the last you'll be seeing of me this term, and you can have a lie-in tomorrow. But let's get going to see if that indeed is borne out. So this lecture will be devoted to a taste of Hamiltonian mechanics. So we spent last week looking at Lagrangian mechanics, and I hope you were convinced it's a very elegant way to re-attack mechanical problems. So the Hamiltonian approach is sort of parallel to that, and as much to recommend it, we'll only dip our toe into it and get a taste, but I hope that taste will be encourage you to look for more in the future. Okay, so let's just get going. If you okay, so Lagrangian mechanics, what it does, said by that first bullet. So what is the difference between Lagrangian and the Hamiltonian approach? Remember, Hamilton was this Irish physicist who actually did a lot to help illuminate Lagrangian mechanics. So in the Lagrangian is a function of these generalized coordinates qk and qk dot, and then we'll move to something called the Hamiltonian, where we don't work in terms of qk and qk dot, but qk and pk, where pk is, we've been dealing with this should be familiar. So this is the conjugate momentum, but if we have several variables in the system, there'll be several of them. And I remind you, I mean, already this is something that we saw, that the conjugate momentum is can be extracted from the Lagrangian in this manner, dl by dqk, and this means that already we could rewrite the Euler-Lagrange equation, could be written as pk dot equals dl by dqk. So we already had some taste of how we could work in terms of these two variables. Okay, so let's try and introduce, let's try and go towards the Hamiltonian. And so this manipulation will be a little formal, but not too difficult. We just need to use the rules of the rules of partial differentiation. So in general, so the Lagrangian again, let me write it, it is a function of t, qk, and qk dot. Now, this is in slight contradiction to the, let me actually modify this ever so slightly. I beg your pardon. If you start, I want qk, which can be a function of t, and qk dot, which can be a function of t. Right. So this is in might look in slight contradiction to this. That's because actually the Lagrangian, I mean, these two generalized coordinates, what's been very clear is that they can vary with time, and so I write them as functions of time to make that point very, very clear. Something which is possible, which I don't actually think we've seen in any example we've looked at, I might be wrong, but the Lagrangian itself can also explicitly depend on t. Okay, so L can explicitly depend on time, whereas qk and qk dot are implicitly functions of time. Okay, so I don't think that is too shocking, but I concede I'm not sure we've had an example where we've actually written time explicitly into the Lagrangian, but you can well imagine that might be the case. So what I want to do is work out what is what we call the total derivative of L with respect to time. And we write that as dL by dt dd. These are not partial d's, okay? So what one needs to do is to remember how the rules of partial differentiation work, and I hope you've been exposed to this in your maths. So let's just write down this rules more generally and then apply it to this question, the problem in hand. So if I have f, which is a function of x, which is a function of y, which itself can be a function of x, and z, which is be a function of x, then what does the total derivative look like? Well, df by dx can be written as the partial derivative of df by dx plus the partial derivative of df by dy multiplied by dy by dx. We write in that term because y is just a function of x, plus dz by dx. Hang on, wait. No, df. No, that's seriously wrong there. Plus df by dz multiplied by dz by dx. Okay. So I hope that looks reasonable to you, and you've probably, and I hope you've even covered that in your maths. But take care to look at where we use curly brackets, curly d's, and when we don't use curly d's. But this should look at least plausible. Right, so let's apply it to the task in hand. So we want to find dl by dt. Dl by dt. So firstly, there's the possibility that L is implicitly dependent on t. So we have that term. And then we have terms of this sort, but we may have more than, k there may not just be restricted to one. We may have several generalized coordinates, okay? So for each generalized coordinate, you get a set of terms like this, and therefore, when you consider everything which can happen, you're going to get a sum of those terms. So the sum, then you get curly dl by dqk multiplied by dqk by dt plus dl by dqk dot multiplied by dqk dot by dt. Okay. Just check it's right. So again, that's nothing more than just copying down this rule of partial differentiation, but allowing for the fact that I have more than one generalized coordinate. Okay. So let's see if we can manipulate this. Well, now let's, before doing that, let's just write it in a slightly more compact manner. So dl, so just repeating dl by dt plus I'll try. So I have the sum again, and I want to, I keep dl by dqk, but the next term, dqk by dt, I'm going to write that as qk dot, no big deal there, and then plus dl by dqk dot, and then the second term becomes qk double dot. Okay, so that's no more complicated. So all that's achieved is I've now been able to write the expression on one line, so that's great. However, we know something about this and this, because we've been manipulating these expressions in the Lagrangian expression. So we've been manipulating these when we've been playing with Euler-Lagrange. So we know, for example, that pk, the generalized, the conjugate momentum, is no more than dl by dqk dot. And we also know that from Euler-Lagrange that pk dot is dl by dqk. Okay, so that's just Euler-Lagrange. Okay, so this is nice because it means we can write this expression in an even more compact manner. This means that dl by dt is equal to partial dl by dt plus the sum, and now the first term is going to give me, so that dl by dqk is going to give me p dot k multiplied by qk dot plus, and then dl by dqk dot, that's going to give, that's nothing more than pk multiplied by qk double dot. Okay, so it's one, you may not know where we're going, but I think we'll agree that things are getting sort of more and more elegant. Now what we have in here, that can easily be seen as a derivative with respect to time of what? Of pk times qk dot. Okay. So now, so if you were to make the differentiation with respect to time of this, you'd first get a dot on here multiplied by qk dot. That's the first term. And then you get a pk multiplied by qk double dot, which is that term. So indeed, this is correct. Okay, so we have a total derivative on the left-hand side. This is also a total derivative because these things are functions of t. So what we can do is move this across to the other side of the equation. So we can say d by dt of L and then minus all of this, so we get the sum of pk qk dot, and that is equal to partial dl by dt. Okay. Now this here we define as the Hamiltonian, or actually minus the Hamiltonian. And we end up with, therefore, that dh by dt is equal to minus dl by dt, where h is the Hamiltonian, and just, you can see what it is, but let me write it out without the minus sign. pk qk dot minus L. Okay. So that was a little formal, I agree, but we've ended up with, at least with this rather nice and compact expression. And now you might say, well, so what? Well, in a moment I'm going to tell you what the Hamiltonian represents, but let's, before doing that, make one immediate observation. Which is that if L itself, if the Lagrangian does not depend explicitly on time, so if your Lagrangian doesn't have t figuring in it explicitly, then the right-hand side of this will disappear, and you'll have dH by dt equals 0, and hence h must be a conserved quantity. Okay? So if L does not depend explicitly on time, then h is a constant of motion. Since dH by dt will be equal to 0. Okay, so that is already, I think you'll agree, you know, what if we can calculate what this is, then we might find out that then we know it's constant for many, many circumstances, and that's is conceivably useful. Now, but I think you need to know more. I think you need to know what this physically represents. So let's try and work this out. So what does the Hamiltonian mean? Okay, so this is the expression we've got, and we know so with the Hamiltonian we want to ideally work in terms of, I mean, Hamiltonian is a function of pk and qk, but it could be built up from pk and qk dot. And we know, if we know a Lagrangian, we can extract these quantities. So let's do that. So for let's take a general case in 3D. So let us build up the Lagrangian, and then from that we will build up the Hamiltonian. So firstly, the kinetic energy, that's T, and in Cartesians that's a half m x dot squared plus y dot squared plus z dot squared. Okay. And so L is just this minus, so let me write this again, x dot squared plus y dot squared plus z dot squared minus some potential, we won't specify it, but it's a function of x, y, and z. Okay. Right, so now we need to work out what the Hamiltonian is. So we know that p x, for example, it's just this divided, this differentiated by x dot, but we know what it is. It's mx dot py equals my dot, etc., that you know. And so the Hamiltonian, okay, so I'm going to now construct this first term here. So I need to multiply the conjugate momentum, so that's just the momentum, multiplied by the velocity. Okay, so it's just mx dot multiplied by x dot. You see, that's what the first term is here. And then similarly for y dot and z dot. And then we have to subtract off this the Lagrangian, which is, let me just keep it as minus T minus U, okay? But if you look at this for a bit, well, it immediately strikes you that this is nothing more than, if I can, twice the kinetic energy, right? That's a half mx squared plus half my squared plus half mz squared multiplied by 2. So we've got, so this Hamiltonian is 2t minus t plus u equals t plus u. So this is nothing more than the total energy. So that's what it physically means. Now, one word of caution, in many systems it will be the total energy, but in some systems e.g. driven systems, and we'll see one of these in a little while, H won't be the total energy. Okay. But that is just in some cases. If you want to understand what the Hamiltonian is, in most cases it's nothing more than the total energy. So I think we can deal with this. So from before, we had dH by dt equals minus dl by dt. So if L not explicitly dependent on T, then what this means, H is conserved, as we said, and so in many systems, but this many is supposed to capture this caveat here, then also E is conserved. So you see, this is rather elegant that we can look at the form of the Lagrangian, and from the Hamiltonian mechanics we can deduce conservation of energy from how this Lagrangian looks. Okay. One other remark is that there's other, you can deduce other conserved quantities from looking at the Hamiltonian. For instance, if a coordinate does not appear in it, then that coordinate is cyclic or ignorable, and the conjugate momentum is a constant of motion. We've already seen this for the Lagrangian. It's equally true for the Hamiltonian, and that will be borne out shortly when we derive Hamilton's equations. And this is already upon us. So in Lagrangian mechanics, you have the Lagrangian, and with that you can apply Euler-Lagrange equation, and from that you get equations of motion. So you can do something similar in Hamiltonian mechanics. So, and this is to arrive at Hamilton's equation. So let us do that now. Okay. So let's be clear that the Hamiltonian, we want to regard it as being just a function of Q and P. Those are the coordinates we want to work in. But if we construct the Hamiltonian, it's built up as it's built up in the form as written there. So if we want to actually build it up, we usually have to start from using not just P and Q, but also Q dot. But Q dot we now will regard as a function of Q and P, right? Because these are the coordinates we want to work in. So, so again, the Hamiltonian is Pi Qi dot minus minus L. That's just as we had it previously. But now let me rewrite this and indicating what each coordinate is a function of. So pi we want to work in that remains as it is, but qi dot, this is a function of q and p, and the Lagrangian is a function of q dot q and p. All right, so why have I done this? Because I now want to differentiate partially the Hamiltonian with respect to momentum. Again, so this lecture will be quite formal, and this is another slide of formalities. After this, things loosen up a bit, so hang on in there. So I want to work out dH by dpk, because there can be several generalized momenta. Let's focus on the k, the k momenta. Okay, so then what do I get? So I operate on this thing here. And so firstly with this term, okay, so this has got two things contributing, pi and qi dot, and there's a sum over them. So firstly operating on the pi, when I is equal to k, then the differential will give me 1, and I'm just left with qi dot. But qi in that case will be qk, right? Let me just write down the term, and then it's easier to explain. Okay, so this is operating on here. We need to worry about what this does on the qi's, but I just want to focus on the first factor in that term. That because I'm differentiating with respect to pk, then the sum will disappear, because when I differentiate with respect to any p, which is pi where I is not equal to k, that will give me a 0. And then the second term will be, I will retain the sum, let me write it, pi dq dot I divided by dpk. Let's just be clear that that part here is the d by dpk acting on that term. Okay, so again, I've said that many times. The manipulation will get rid of the sum here, but we'll pick out q dot k. Here, that won't happen, but we have a differential of dqi dot with respect to dpk. Right, so this is the real exercise in your partial differentiation. We now have to worry about the second, the Lagrangian part, and so we have minus dl by dpk. Okay. So let's write this again and try and simplify things. So the first two terms I'll for now leave just as they are. So it's qk dot plus the sum over I pi dqi dot by dpk. But this second term, more chalk needed, I can write as minus dl by dk. Yeah, so the deal is that the Lagrangian is not explicitly dependent on pk, it's explicitly dependent on q and q dot, but q dot can be a function of p, so that second term can be written as the sum over dl by dqi dot dqi qi dot divided by dpk. Okay. So again, because L is a function of P and Q, so if L is a function of Q and Q dot, so I need to express it in these terms. Okay, so things start to get easier now. So let's remember again what the definition of the conjugate momentum is, or how it's related to the Lagrangian, that Pi is equal to dL by dQi dot. So that means we can write that term more simply. So we end up with qk dot plus, again I'm keeping the first terms unchanged, but the last term becomes minus the sum over Pi dQi by dpk. And that's great, because that term, so now that looks just the same as this, and so we can cancel them, and so we end up with dH by dpk is equal to qk dot. Okay. So that's one of Hamilton's equations. So all we've done is do a partial. So the Hamiltonian depends on qk and pk, so it's natural to want to differentiate with respect to each of them. We've now done it with respect to pk, and we've got this compact expression. You can do just the same sort of manipulation, but I think we'll all agree that rather than go through it, we'll just leave that on the slide. But what we would also like to do is work out what dH, but with respect to dQk is, and that turns out to be minus pk dot. Again, a very compact expression. Okay. So what have we got here? So with remember, with the Lagrangian, we had the Euler-Lagrange equations, and those are second-order differential equations. And if we had n generalized coordinates, we had n Euler-Lagrange equations. So we have something which is similar but different here, which is that if we have n sets of generalized coordinates, we will have 2 times n first-order differential equations, which are the Hamiltonian equations. Okay. So our alternative way of solving a mechanical problem is to write down the Hamiltonian and then to write down these equations and solve these and see what they tell us about what's happening in the system. One can also see embedded in here that there are symmetries. This business about if the Hamiltonian is, if a variable is a coordinate is cyclic, that means if it doesn't appear in the Hamiltonian, for example, if qk does not, if the qk does not appear in the Hamiltonian, then the left-hand side of this will be 0, and the differential of the conjugate momentum with respect to time will be 0, hence the conjugate momentum will be conserved. Okay, so you can already see this by looking at the right-hand side of this equation. So if h not dependent on qk, i.e. qk is cyclic, then pk dot equals 0, and pk is conserved. And you see that there's actually a similar statements you can deduce from looking at the other equation, but we won't go further into that. This is just dipping our toe into the vast ocean of Hamiltonian mechanics. Okay, let's just, having derived these equations, we should use them at least once, and so we'll do that, but as I say, we will not be going into this with anything like the enthusiasm or time we did for the Lagrangian, but let's use it, let's look at it once. So let's consider a central conservative force. Okay, so we've done all the heavy lifting in terms of the partial differentiation now. It should be everything should be nice. So the Lagrangian for such a force, we've written this many times, it's a half m r dot squared plus a half m r squared theta dot squared minus v, which is a function of r. So that's the Lagrangian. What about the Hamiltonian? So the Hamiltonian H, let's remind ourselves again how H is written. Yeah, so it's on the, it's maybe even easier to see, the top of that slide. So we need to sum over the momenta in the game for each coordinate. So we have the r dot coordinate. So we have we have the momentum associated with r, so that is p subscript r multiplied by r dot, and then we must have also worry about the theta coordinate, so we have p theta multiplied by theta dot, and then minus the Lagrangian. Okay. So the first thing we can say is that there's no explicit t dependence. You don't see t in this expression, so we know that h is conserved, and one can immediately convince yourselves that in this case h is in fact the total energy. So no explicit t dependence, so h and E conserved. Okay, but let's go further with this. Let's try and work out, write this out more fully. So we know that PR, so we want to write the Lagrangian, it really should be written in terms of the momentum, in terms of the PKs and the QKs. So we'd like to eliminate the R dots. Okay, so we know that R dot, what is that? Well, that's, I can just write that as the radial momentum divided by the mass, PR over M. That's obvious, right? And similarly, theta dot, we know that also that well, p theta is going to be given, the angular momentum will be given by m r squared theta dot. So theta dot is p theta over m r squared. Hence we can write the full expression for the Hamiltonian as p squared, pr squared over 2m plus p theta squared over 2m r squared plus v of r. Okay, so you right, so yeah, that should be clear. I maybe should have written one intermediate step, which is the, again, if you were to, let me verbally give you the intermediate step. So that all I've done here is substitute this into these two terms, and these two terms will have given me two terms which are obviously twice the kinetic energy. Okay, so this first term will give me, for example, PR squared over m. This will give me p theta squared over mr squared. But then when I subtract off the Lagrangian itself has the kinetic energy in it. So I get twice the kinetic energy minus the kinetic energy. And so I get these two terms with a half in them. Okay, so this is just no more than the Ke. And we get the potential energy with the positive sign in front. Right, so now consider Hamilton's equations. So firstly, let's consider these ones, which is that qk dot is equal to dh by dpk. Okay, that was one of the two. So we're going to have one of these for r and one for theta. So this gives us that r dot is equal to dh by dp subscript r, which is going to just give me pr over m. And similarly, theta dot will be dh by dp theta. That's just going to give me p theta over m. Okay, so these are, let me give these a number 1 and 2. So these are just, so these just reproduce 1 and 2. Okay, so this is not very exciting, but it's good to see that information is there. Now let's, we have this other Hamiltonian equation, right, which is that also we have that dh by dqk is equal to minus pk dot. So let's see what that gives us. So in the r case, this is going to give me that minus pr dot is equal to dh by dr. What is dh by dr? Well, we're going to have minus p theta squared over 2 over m r to the cubed. Plus dv by dr. Okay, let's call this equation 3. And we will also then have the, for minus p theta dot, that's going to be dh by d theta, which is going to be 0. Let's call that equation 4. So these are these two equations, even with the same numbers. So firstly, let's concentrate on what 4 tells us. This we could have seen straight away. Because theta didn't depend on, because the Hamiltonian didn't depend on theta, we see that p theta dot is 0, so p theta, which is the angular momentum, is conserved. Okay, so this, so the conservation of angular momentum is seen from Hamilton's equations and the fact that h doesn't depend on theta. This equation, the top equation 3. Okay, so 3, so 4 gives us conservation of angular momentum, and 3 gives us the equation of motion in R, which is the sort of thing we were considering for many weeks when we were doing orbits. So let me just write down exactly what this 3 is. I just restate that. So that's mr double dot equals j squared over mr cubed minus dv by dr. Okay. So this is the equation of motion. This we would, if we were starting from scratch, we can integrate this if we wished, but we won't do that today because we considered equations of motion for orbital momentum, for orbital motion at length for several weeks. So no need to go back to that, but just to remind you that everything is there. Okay. So just to convince you that this expression should look relatable to expressions we've dealt with before, if we compare with our familiar energy equation, that is just E is equal to a half mr dot squared plus j squared over 2mr squared plus v of r. Okay, so that's the energy equation for a central force, a central potential. Let's differentiate that with respect to time, dE by dt. What do we end up with? We end up with mr dot r double dot minus j squared over 2j squared over mr cubed r dot plus dv by dr r dot, and this we know, we said on the previous slide that this is equal to 0 since E conserved. So we have that 0 is, and if we take out r dot, we have mr double dot minus j squared over mr cubed plus dv by dr. Okay, and everything here, this is the same as, this is equation 4. So all I've done is to show you that that equation 4 from Hamilton's equation is entirely consistent with what we also know, what we've known about from other directions from the consideration of central potentials. So Hamiltonian contains all the knowledge on the system. Okay. Great. Right, so I think we'll pause there. I think just to give you some sense of what's going on, we need to talk briefly about a couple of examples we've dealt with already. So we will come back to this bead on a hoop and look at this from the Hamiltonian perspective. But we'll do that in an hour's time after your optics, if you indeed have optics, and after I've had a cup of coffee. So I'll see you a bit later.